So today we are going to talk about the membrane transport and also about the membrane potential, and we are going to calculate it. I also have prepared for you some self-activities. The optional activities for today for you will be to calculate five examples. So let's start, I think. So everybody is here. Nice. Okay. Okay. So just remember, not before lecture, but the lecture 2 weeks before, we finished our speech about the membrane content. So we just briefly mention what is the role of phospholipids, what is the role of cholesterol, membrane proteins, the signalization coming from sugars. So this is just a nice picture of the mosaic, which the membrane is sometimes called. 2/3 of the plasma membrane is consisted from phospholipids. In this case, it's these blue heads with 2 tails. So these balls, just remember that this is the phospholipid head, and these 2 tails, it's fatty acids. So it means that the surface of the plasma membrane, I mean this surface, this is the maybe the extracellular space, and this is intra. These parts and this part, this is water soluble, so it means it is polar head. So it means it can be dissolved in water. It has a contact with water. Water is inside the cell as well as outside the cell. However, the inner part of the plasma membrane, which is created by these fatty acid tails, it's insoluble in water. We are talking about the non-polar part of plasma membrane. So 1/3 as 2/3 is phospholipids. 1/3 is cholesterol. 1/3 is cholesterol. So very important molecule for humans. Plants, they have ergosterol. Bacteria, they have hopanoids. So as we mentioned before. And approximately from 1 to 3% of the plasma membrane content is created by proteins. So there are several types of membrane proteins. They are merged into the plasma membrane. They merge in both sides. They can merge only in one side. Integral membrane proteins, many of them, membrane channels, and so on. Moreover, there are these sugar parts, these little oligosaccharides. This is for the signalization of plasma membrane, signalization or cell signalization, for the communication between cells, and also for the recognition of our immune system, as well as recognition for some viruses and bacteria. So this is like a QR code of every cell in our body. Today we are going to talk about, just briefly, because I think we will need more time for calculations. So I just briefly mentioned the types of transport. Not only secondary transport, but all transports, all of them. Briefly, I will mention the membrane transporters, and we will talk about the resting or equilibrium membrane potential. So resting or equilibrium potential. We are going to talk briefly about the theory and share about the calculations, so applications, how to calculate it. And in the end, maybe last 20 minutes, you will you can use this time for your own calculations, just proving that you understood pretty well. And for this purpose, I just prepared some mini tests in Google Forms, as you know from previous cases. You will have time to calculate it, the examples until next Friday. So I think it's a lot of time. If you didn't understood for the first time, just see the video again and again, and we will see. So first of all, I don't know what happened. I missed some. I missed some slides. I don't know what happened. Okay, maybe I can make it a little bit easier. Okay, let's make a just little overview. I will also give you a video, separate video, which is something like 80 minutes, and it concludes everything together. So we have two types of transport. The first one is spontaneous, and it doesn't need any energy. We are talking about diffusion. Actually it is not without energy. The driving force for this energy, for this process, is the concentration gradient. So it means that, for example, we have a chamber, a room, which is full of students, and the doors and windows is closed. The students cannot really escape from this chamber. And so actually, if I put there another chamber which is empty, and I open the door between the full chamber and the empty chamber, spontaneously students from the full chamber will move on to the empty chamber. So it means that they will go along the concentration gradient from the space of the higher concentration to the space of lower concentration. The same scheme can be applied also for molecules, atoms, particles, gases, and so on. So particles spontaneously move from their place of higher concentration to the place of their lower concentration. We are talking about passive diffusion. Is it clear to everyone?
Yes. Yes.
Okay, but sometimes they need some help. They are allowed to move from their higher concentration to the lower concentration. However, they have some mobile problems. For example, some people with handicap, it's not easy for them to just enter to some buildings which are stairs and so on. So they need some elevators, at least someone who will assist them. So it's the same like with these particles and molecules. Some of these molecules, they are not really passing smoothly across a barrier. They need actually some help, some carrier. So the carrier could be a channel or some molecule which can capture the molecule and just to transfer it across the plasma membrane and open. So it's the same like with people. We are talking about so-called assisted diffusion or mediated diffusion. This is all synonyms. So if it is written in this picture, the case number 1, as the simple diffusion, no assistance is needed. So the driving force is the concentration gradient. And this second case, again, along the concentration gradient. The driving force is concentration gradient. However, the particles are not going smoothly across the barrier. In this case, it's a membrane. They need some assistance. There are two cases of this assistance, a pore, this one, pore. So it's a mediated diffusion and cross channel, or it could be a carrier, which can be a molecule which just flip-flop the barrier. And we are also talking about mediated transport, but not it's a channel, it's something like a carrier. So this is the first type. So no ATP, no energy. Yeah, no ATP, no energy, just concentration gradient, only concentration, only concentration. It's concentration. Okay, the second type of transport is called active transport. It means that the particles are moving against their concentration gradient, from their lower concentration to the higher concentration. And because it's, you feel it that it's not really natural, just try to imagine the situation. We have two chambers. One chamber is completely full of students. The second one, there are just few or three students, and we would like to push these three students to the completely full chamber. They will probably protest, and we will need a lot of energy to push them to the full messy chamber from the empty chamber. So is it clear, this mental imagination?
Yep.
Okay.
Yes.
Great. So the sources could be the various energies. So first of all, very well known is ATP. Also light, it's a good source of energy to just move particles against concentration gradient, or ion gradient. So it means it's just a type of the secondary transport, ion gradient. It means that I am using the electrochemical gradient of some different particle to move some another particles against their concentration gradient. Just example, during the membrane phosphorylation, you mean in mitochondria, the oxidation, creation of ATP. We are using the gradient of protons of H plus molecules to phosphorylate or synthesize the ATP molecule. We are talking about the membrane phosphorylation of ATP. So we are using the concentration gradient of a different particle to move and synthesize or provide some work of a different article. So therefore we are talking about the secondary transport. So the driving force for secondary transport, it's usually the electrochemical gradient. Questions? Okay, no questions, so that's good that everything is clear. Now I would like to move to the membrane potential. Probably you know that the majority of practically all living cells, they have some charge inside the cell and outside the cell. And the difference between the charges gives one special feature to the plasma membrane. We are talking about potential. So what is potential? If we separate two charges, like just imagine a battery, there is a plus and minus, and because of they are separated to plus and minus, between them there is create a potential. It's some energy which can be used for something. It's the same like with the plasma membrane. We have just, I will return it a little bit back. Here we have plasma membrane, inner part and outer part of plasma membrane, and this part is charged negatively, and this part is charged positively. And because the charges are separated on two sides, so in between there is an insulated, and this is really insulator because it's there is no it's fatty acid, so it's like a fat. If you would like to insulate something in electro engineering, you will put there plastic or fats. It's a good insulator. So these two charges are insulated and separated, and between them is created a potential. Questions? During the resting membrane state or equilibrium membrane potential, we are talking about the negatively charged inner space of every living cell. So it means that inside the cell there is a negative charge and outside the cell is a positive charge. The difference between these two charges give to the majority of cells a potential, membrane potential, ranging between -50 to -90 millivolts. So minus, it's a negative potential. This value is typical for the resting membrane potential. So how it is created, that's the crucial point. Just imagine a cell. Yeah, this is a plasma membrane, this green line, gray inside the cell, white outside the cell. So extracellular space is white, intracellular space is gray in this case. How the differentiation or separation of charges on two sides of plasma membrane is occurred. We have 4 players which give us the opportunity to separate the charges on both sides of the plasma membrane. So do you have any idea which 4 players they are? It's ions. First one, it's organic molecules. It's actually the 5th player. It's in general, all organic molecules. Normally, inside the cell, there is a higher concentration of molecules, organic molecules, in contrast to the outer space of the plasma membrane, yeah, extracellular space. And if we just make some average of charging of these molecules, the dominant charge of organic molecules is negative. So we will just a little bit simplify it, and we will say that simplify it. It doesn't mean that all organic molecules have only a negative charge. However, in this case, just to simplify, just consider that the majority of them, they really do. They have a negative charge. This is inside the molecule. Inside the molecule, also, we have a potassium cation. So it means that potassium cation is a very little atom. It's a ion, cation. It has a charge +1. The majority of potassium in the resting membrane state is placed inside the cell. I can really recommend you to take a pen or pencil and just draw with me what I'm telling you. This is a crucial point of next 2 lectures. So please follow me. I am going to talk slowly and just try to draw it. Outside the cell, there is of course a little bit of potassium because, you know, the leaking of the channels, it's not really evacuated, and also some leaking is possible. So outside the cell is also potassium, but the contrast, it's, you know, there's a difference in orders. Yeah. So it means that the positive charge of potassium is stabilized by the negative charge of organic molecules. So it means that that potassium, because of it has a positive charge, is captured inside the cell because of the negative charge carried by organic molecules. This is the first point. So the negative charge in the cell stabilizes the positive charge coming from potassium. On the other hand, because of the higher concentration of potassium inside the cell, there is a big concentration gradient, which really forces potassium to coming out the cell. So normally, without the stabilization of the negative charge coming from organic molecules, potassium would leak outside the cell. However, because of the organic molecules, potassium is captured inside. What else is there? There is sodium. In contrast to potassium, it's also a cation with charge +1. However, sodium is placed outside the cell. Inside the cell, we can find also some few sodium atoms or cations. the reason, so sodium is really an ion which would like to enter to the cell because of the concentration gradient. This is the first force. And also because of its concentration gradient. So there are two forces pushing sodium inside the cell. The charge, because of inside the cell there is a negative charge, and because of the concentration gradient. However, plasma membrane is a barrier, effective barrier, which membrane potential normally closed for sodium at all. So sodium channels are closed normally, and the sodium-potassium pump is just recovering this different distribution of ions because it's pumping sodium outside the cell and potassium inside the cell. Another is calcium. In contrast to sodium and potassium, calcium has two charges, charge plus 2, and its higher concentration is outside the cell and its lower concentration is inside the cell. So the forces are similar to which influence the behavior of calcium is the same like for sodium. So it means that calcium would like to go to the cell because of the negative charge in the cell and because of its concentration gradient. But normally, as you know probably, during the resting membrane state, also the calcium channels are closed. And finally, the last player of this resting membrane potential picture is a chlorine. Chlorine adds an anion, so it means that his charge is -1, -1. So its concentration is higher outside the cell. In contrast, its concentration inside the cell. So the concentration gradient just pushing chlorine to the cell. On the other hand, because of the negative charge inside the cell, it has a contradictory effect to the movement of chlorines, because inside is a negative and chlorine is really not attracted inside the cell because the same charges have repulsions, minus and minus is repulsive forces, as well as plus and plus is repulsive. Only plus and minus, they are attracting together. Questions? Okay, I think everything is clear. Sure.
Yes.
Okay, good.
Yes. Yes.
So, okay. Thank you for the feedback. Sometimes I'm not sure if I'm still online or if you are not sleeping there. So thank you for every word you can tell me. So how it looks like. Why we have this distribution of ions? The reasons are evolutionary. We spoke in the first lecture how life was created, that probably it was created in the water, in the seawater. So that's the reason that the concentration and content of intracellular and extracellular water, it's quite similar. If we just look at this table, we can see that the concentration which is inside the cell, so intracellular concentration, so from the point of view of potassium, higher concentration, so I will make maybe like this one. For sodium, it's a low concentration. For chlorine, low concentration. For organic ions, a high concentration. For calcium, lower concentration. In contrast to the seawater or extracellular space. So potassium is low. Sodium is very high. Chlorine is also very high. There are practically no organic anions, more or less. it's approximation, of course, and the calcium is also higher. So this is the absolute values. If we just look at the ratio between internal or intracellular and extracellular concentration of potassium, you will see that 20 to 1 approximately for sodium, 1 to 10 approximately, the same for chlorine, 1 to 10. Organic anions, it cannot be because we cannot divide with 0. And if you look at the calcium, we will see that it's approximately 1 to 25. So it's very good to keep in mind these values, because these values are more or less the same for all animals, not only for seawater or sepias living in seawater. This is for sepia, the values, this is exact values, but more or less the same values have also humans, monkeys, and other animals. So first of all, just how to calculate but how to know the resting membrane potential value. There are two approaches. The first one is an experimental approach. We can measure the potential. So first one is measure. For the measurement of the plasma membrane potential, we use a special electrochemical technique, which is called patch clamp. So the patch clamp technique, maybe I will find in Google a picture. Okay, I think this picture is also a good one. Okay. Oh. This one is it enough big for you, this picture?
Yeah, we can see it.
Yes.
Okay. This is a cell. This is a microelectrode. We also are talking about micropipettes. So it's a glassy pipette, which has very tiny and narrow tip, around several micrometers. So this electrode, so the pipette is filled by electrolyte, and also there is a wire like an electrode. We just put or suck the electrode on the surface of plasma membrane, and we can monitor and quite precisely measure the changes of the potential, just to measure the currents which are going or changing in the membrane. So also not only the resting membrane potential, but also the action membrane potential can be measured. All the changes of the plasma membrane potential can be detected by this system. So this is the measure electrode, and also we also have another, just because in electrochemistry you cannot really measure the absolute values, you measure the difference. So you need at least one electrode which serves as an earth or as a comparison for the measuring values, something which is stable. We are talking about some reference electrode which is immersed to some reference solution. So this is just briefly the background, but we have several types of these measurements. The first one is that we just suck on the pipette on the surface of plasma membrane, as I mentioned before, is that the pipette is sharp and it penetrates the plasma membrane and it is immersed into the cell. So what is monitored by this type of setup is the changes inside the cell. So two types of measurements. on the surface or inside a cell, so two types. So by this way, we can clearly measure the changes of currents which are changing inside or outside a cell. The range or the value of currents which are in cell, it's in range of picoamperes. So this is the experiment, and now we are going back to calculations. So the second way how to gain the value of resting membrane or action membrane potential indeed is calculations. So calculations, this is the second type, calculations. Calculations. So for the calculations, we are using Nernst-Peters equation. If this equation is applied to some physiological systems, we are talking about Nernst-Peters-Goldman-Hodgkin-Katz equation. So Nernst-Peters, it was electrochemist or physical chemist in original, and they provide this equation for some electrode systems. However, Goldman, Hodgkin, and Katz, these three scientists, they apply the same equation to some physiological systems. So I think it's better to call it Goldman, Hodgkin, Katz, Nernst-Peters equation. But for you, I think it's enough just to remember Nernst-Peters equation is the same equation. Yeah. So what is inside? So air, it's ER. It's the resting membrane potential or membrane potential in general. R, it's the universal gas constant. T, it's the absolute, it's temperature or absolute temperature expressed in kelvins. Z, it's the charge of the particle, which we are calculating the contribution to the membrane potential. So in this case, it's a charge of potassium. So the value of Z in this case, Eva, do you know it?
Potassium.
I'm asking for the value of the Z number of potassium.
+1.
Yes. Okay. And F is the Faraday constant. Ln, it's the mathematical operator called natural logarithm. And potassium in these brackets, outside and inside, is the concentration of potassium outside the cell, so in extracellular space, extra, sometimes there is an E, or intracellular space, so the concentration inside the cell is down, and up is the concentration outside the cell. Maybe a little bit more detail. So sorry for coughing, but everybody in our department has COVID. Only me and the secretary, we don't have it. Maybe we have something else, because yes, 2 days before I was in PCR just to have some confirmation. It's quite funny because we all are vaccinated, and in spite of vaccination, COVID is winning. Okay, what about the universal gas constant? It's R, this one, and its value is 8,314 joules per Kelvin per mole. So do you know what is joule? This is the unit for what about Sunny? Are you there?
She's not taking course anymore.
Aha, yeah, I forgot. Okay, Katarina, what is the abbreviation for joule or J? J is for
Joules is for power.
yes, for power or work. So what about Marek? Kelvin, what is the unit for?
Kelvin is the standard measurement of temperature.
Yes, for absolute temperature, and maybe CMin. Are you there? What is mole?
Is quality.
It's
Is the materials the we.
okay. It's actually the amount of particles which is given by the
1 more equals 6.02 times 1023. But I don't know in English. I forgot.
yeah, it's fine. It's Avogadro number. I know. It's okay. So Avogadro, just remember the points. One correct answer, 1 point. Just remember that, and you will tell it to me, and I can give it to you. Yeah, just okay. Siemin has 1 point. Marek 1 point. Eva 1 point. Katarina 1 point. Someone else? Okay, just remember that. Yeah. Okay, so this is the universal gas constant. It's not necessary to remember the value because you have it in a calculator. You can find it elsewhere. And if you are going to calculate the value of resting membrane potential, I will give it you this number. So what about temperature? Normally, you know the temperature, okay, in the ambient temperature, in room temperature, it's something like 20, 22 degrees of Celsius. In Europe and in America, they use Fahrenheit. However, in physics and chemistry and biology as well, we which is expressed as absolute temperature, so in kelvins. So key is Kelvin. So because the temperature, which in Celsius, for example, it's really the relative value, and it was derived from the values for water, freezing point of water and boiling point of water. This is the grade between 0 and 100. Yeah, this is the Celsius degree. And it is expected that the absolute value, absolute zero, is the temperature which is in some parts in our universe. So we cannot have lower temperature than is 0 kelvins. We know that in the majority of our universe, the temperature is around 4 kelvins. So 4 kelvins in the majority of universe, and in some space, like in some universe, in some parts of universe, we expect that there is an absolute zero, null Kelvin. So how to express normal temperature? So for example, here I have 22 degrees of Celsius. So I would like to convert it to kelvins. How I can do it? Oh, this simple mathematical operation. So this one here, I think this can be neglected for our purpose. So in Kelvin, the room temperature is 295 kelvins. So who didn't speak? I have to see which students I have here. Okay. Marek, Siemin, Katarina, Eva, Mariam is here. So Mariam, please, could you tell me what is the value of absolute temperature of our physiological temperature? So physiological temperature 37. So how to express it in kelvins? Just tell me the value. So it means I would like to
37 plus yeah, sorry, 273, and it's equal 310.
Yes, very good. So physiological temperature, maybe I will write it here, 37 plus 273 is 310 kelvins. Very good. So you have also a point. Maybe I will make. Okay. Okay. So that's clear. Yeah. So if I tell you that you will use absolute, so you will use a scale of absolute temperature and you are going to calculate this physiological temperature, you will know that it's 310 kelvins. Okay, so that number, so tell me, so for potassium, that number is +1, so this is for potassium. So what about for sodium? What about Marek?
Also +1?
Yes, another point, so +1. For chlorine, Mariam?
It's -1.
Yes, very good. And Katarina, what about calcium?
+2.
Yes, very good, +2. Okay, Mariam, Katarina. Okay. So Faraday constant, it's a constant, so it's not necessary to remember. This constant is expressed in coulombs per mole. So coulombs, it's a charge per some mass unit. This is not so interesting, but what is interesting is these two variables, they are changing. They may be different in different cells. So in this case, we are just consider potassium. However, as you recognize later, we will calculate with all ions, not only with potassium, but at the beginning just potassium. So concentration outside the cell, so extracellular space, this is the value, okay, in mole per liter, or alternatively, it could be in millimole per liter, mole per liter. The concentration inside the cell in intracellular space, so it's this one, and again in mole per liter or millimole per liter alternatively. Questions? Okay, clear, good. Oh, who's that? From last year. So now just take a calculator. Just get ready for first calculations. So calculate the value of the equilibrium potential or resting membrane potential, it's the synonyms, in millivolts on the cell membrane at physiological temperature. So what is the physiological temperature, Xiamin? In kelvins. I mean, human physiological temperature.
I know, plus 217, right?
I think Mariam just calculated. Just tell the value if you remember.
It's 293.
Eva, do you know the physiological temperature of humans expressed in kelvins?
It's 310.15 kelvins.
Yeah, I think 310 is enough for our purpose. Okay. So this is our first number. Then the intracellular concentration of potassium is 350 millimole per liter. The extracellular concentration is 10 millimole per liter. Also assume that potassium as the membrane for potassium is ideally permeable, so it means that it can go through. And also the gas constant is this value, and the Faraday constant this value. So There's only one thing that you have to remember. It's the value. It's the formulation for the Nernst-Peters equation. So it's that one. So please take a paper and a pen and maybe follow my calculations. I think this is the best way how to learn it. And now we will put just numbers which we know to our equations. So resting membrane potential is our unknown. We are going to calculate it. Here is the gas constant. So it's that one. That one. Z number is the charge of potassium in this case, +1. I will change the color. So T, it's 310. The temperature in kelvins. F is the Faraday constant. And also here, here is the extracellular concentration of potassium, and here is the intracellular concentration of potassium. This one is the natural logarithm, it's the mathematical operator. Do you know another type of logarithm? CMN. So natural, and the second type is
sorry, can you repeat?
so we have some mathematical operators like functions. So natural logarithm ln. Do you know another type of logarithm? Not the natural.
Log 10.
Yes, it's decadic logarithm. Okay, thank you. So in this, there is also a variant of Nernst-Peters equation for the decadic logarithm, but I like more this natural one. So the base for natural logarithm, it's Euler number. I think it's something like 2.3 and something. For the decadic logarithm, the base is 10. So now just calculate here. So this part, it's here. Bottom part, it's here, and this is just a natural logarithm. Now just calculate the ln 0,0286, multiply by this part, and you will have these two. Just multiply these two numbers, and the result is in millivolts. It's 0.0595 volts. However, I would like to see the result in millivolts, so you have to shift the comma for 3 places, 3 digits. So in millivolts is -95 millivolts. Questions? Okay, if you have no question, we will continue. Calculate the value of the equilibrium potential or resting membrane potential on the cell membrane at physiological temperature, 310, when you know that the intracellular concentration of chlorine is 50 nanomole per liter, extracellular concentration of chlorine is 500 millimole per liter. Also assume that chlorine is ideally permeable for ion chlorine, and also you know the values of the gas constant and Faraday constant. Please do it for your own. I will just put here only the Nernst-Peters equation, and please put the numbers first to the equations. Okay. If you are ready, just say ready.
Ready.
Okay. So we have probably something like that. Please use your calculator and try to calculate it. If you are ready, say ready. Do not forget that there is a minus. Mariam, are you ready?
Yeah.
Yes.
So you have something like this. Probably I do it step by step because probably you see it first time in your life. So it's better to do it step by step. But for sure, if you are going to calculate the homework, it's not necessary to write there all steps, just the number in millivolts. Yeah. So another step. And once you have a result, just tell me the value. So who will the first one? This person will get a point.
So it's minus
minus 61.
5.
So who was the first one? It was Mariam, I think.
Yes.
Okay. So Mariam, you have another point. It was correct. So don't worry, you will have another chance. So minus 62 millivolts. So please express. You have to read. Yeah, you have to read this text and always look what I am asking. Here I think the calculate the value. So in this in this text it's not written that I want it in millivolts. However, in the homework I put it everywhere. So always write the value of the membrane potential in millivolts. So you have to convert it from volts to millivolts. And please do not forget to if it is minus, yeah, minus plus is not writing, so just minus or plus. So let's start another one. So please read it for your own and try to calculate it. And maybe once you are start to tell me the results, just say your name. So say your name and then the value of the potential before. Thanks.
I think I have an answer.
Yes. Name?
Katarina.
Katarina. Yes. Tell me the answer.
It's minus 65.
minus 65. Ooh. Yes, it's not minus.
Plus.
Yeah. Did you put in the correct order here? You know, the extracellular concentration for sodium is higher than the intracellular. It's the opposite than potassium. Maybe that was the mistake?
Yes.
Okay. Don't worry, you will have another chance. So maybe I will leave it here for a minute just to give the rest of the class just to repair. Just carefully read what is written in the text and carefully put the values. Yeah. Okay. Intracellular concentration, extracellular concentration here. Yeah. Yeah. Okay. Another one. Get ready. So calculate the value for. Do not forget the charge of calcium. So it's +2. Yeah. So here you have the equation. So take your time and try to do it.
I have the answer.
Yes, Marek?
Yes, 57 millivolts.
57. Yes, Marek. Another point. So that's nice. So also everyone has the same result?
Yes.
Yes.
Okay, good. So now you have for your own, just take a few minutes and calculate the resting membrane potential. So I expect that you already have in your memory or in your some written notes the Nernst-Peters equation. Now calculate the membrane potential for these three contributions. Yeah, and who will the first one, and just tell me the correct answers, will receive 2 points. Yeah, so try to do it. So the concentration, the temperature is the same one, 310 kelvins. The gas constant you have in previous cases, so it's 8,3. Faraday constant is 96, something like that. I hope so. So just maybe look at the notes. I will just check it. Yes. Yeah, good. Okay. So 5 minutes or 7. Maybe I have one tip. Write the answers, the numbers, just into chat, so I can give more points to more people. So yeah, just write. So air of potassium is blah blah blah. Yeah, just write it to the chat. Thanks.
I don't have access to the chat. Where can I send it?
Or if you have problem to find a chat, just tell it to me. You have it.
Yes.
Yes.
You can just wait. I will find it. Chat. I have chat here. If I click here, here is a chat.
It says that it's only enabled for like team members. I don't know what it means.
And you are not a team member. Mm-hmm.
I don't think so.
Yeah, it's the same.
Okay, so so first what I said is well, so who will the first one, this one, and correct this student get the points. Sorry.
Excuse me, do we have to send it or what we have to do?
I feel if you just finish, just tell me the numbers.
Oh, okay. So I have them.
So who is speaking?
Mariam.
Mariam. Okay, Mariam, please tell me the first number. I will just write it.
Minus 68.
68. Yes. Second one.
6.6 because it was like multiplied 10 4. I don't know how to say it in English, that one.
No,
but it's 0.76.
It should be simple, like 86, something like that.
Mm-hmm. So maybe I did something here.
Okay, the third one.
It's minus 67.
67, yeah, and the last one for calcium.
43.
43. Okay. Someone else?
Yeah, the last one is 44.
Mm-hmm. It's okay. You have the same values? Minus
yeah,
6.
Another 3 is same.
And what about the second number for sodium? Because
53.
53, 50, yeah. Okay. So let's see. 6 minus 86, it's correct for Mariam. Was Xiamin? Or who was speaking the second one? I cannot recognize you.
I answered the second
one. Okay, so it was correct. So I'm going to give 2 points to Xiamin and Mariam 1.5. Okay, 1.5. So
okay, thank you.
You are welcome. Okay, guys, I think you did a very good job, but we are going to continue with some more complicated calculations next time. Until next time, please, I just send you an email with your homework. It's an optional homework. You can use your 24 minutes of this lecture. I think more or less, I think 24 minutes. It's, I think, very good time to calculate 5 examples. You have the link in your email. So the formula, it looks like that. So do you have it in email?
Yes.
I have.
Okay. So do not forget to write there your name. So this is the first point actually. And then here you have just write here just a number. Yeah. For example, minus 68 millivolts. Yeah. Just this very short answer. Do not calculate there or write here something more complicated. It's not possible to write here more, but write there always the value of resting membrane potential or equilibrium potential in millivolts, yeah, as you see here. Questions? No. Okay, so that's everything. That's all from me today. I wish you a nice weekend, and I will give you the points which you gain. You gain lots of points today. So see you. Bye bye. Have a nice weekend.
Thank you.
Bye
Bye
bye.
bye.
Thank you. Goodbye.
Bye. Thank you.